All right, hey guys, so volume 3, let's get into it. So light always travels at the speed of light in a vacuum. No, that is not true. It travels at different speeds depending on the index of refraction of the substance that it's in. Whenever we're calculating the angles of reflection or refraction, we always measure relative to the normal. So that's this dotted line that I've drawn here. That's perpendicular to the surface of the substance. So if it's flat, that would just be a vertical line. When light strikes the boundary between two substances, it usually reflects and refracts simultaneously, unless there's total internal reflection. White light is a combination of all of the different frequencies of visible light. When light travels between 2 points, it always takes the quickest path, not the shortest path. So that's just in one substance, those will be the same. But if it travels from a point in one substance to a point in another substance, those will be different. So that's called Fermat's principle of least time. Light can only experience total internal reflection when it's traveling from a medium with a large index of refraction to one with a smaller one. So for instance, glass to air, it can experience total internal reflection if the angle is greater than the critical angle, but it cannot happen going from air to glass. So it has to be going from a substance with a large index of refraction to a substance with a lower one. And rainbows are caused by dispersion. So this is the same effect that makes you see a rainbow whenever you shine light through a prism. And dispersion is just a fancy word for the index of refraction actually being a function of the wavelength. So different wavelengths, in other words, different colors, have slightly different indices of refraction. Okay, so light is initially traveling in air when it strikes the boundary between air and an unknown substance, and it has an angle of incidence of 12 degrees. What is the angle of reflection? Well, it's also 12 degrees. The angle of reflection is always the same as the angle of incidence. Okay. Now, if the angle of refraction is 9 degrees, then what is the index of refraction? Well, refraction obeys Snell's law, which says that the index of refraction times the sine of the incidence angle has to be equal to the index of refraction of the second substance times the sine of the refracted angle. So we know both the incident and the refracted angles, so we can solve for the unknown index of refraction. And we get 1.33, which happens to be the index of refraction of water. Okay. What is the critical angle between glass and air? Well, if we just use Snell's law here, the critical angle occurs when the outgoing angle, the refracted angle, is 90 degrees. So sine of 90 is 1. And so the critical angle is the arc sine of the ratio of the indices of refraction. So in our case, we want to know between glass and air. Like we talked about before, it can only happen going from glass to air. So that means we have to put air's index of refraction on top. So it's arc sine of 1 over 1.52. And that gives you an angle of 41.1 degrees. So if you try to do it the other way, you're going to get a calculator error because sine is bounded between 1 and -1. So if you took the arc sine of 1.52 over 1, that's more than 1. There are no real values at which sine has that number. Okay, so light is traveling in glass and strikes the boundary between glass and air at an angle of 1.5 degrees more than the critical angle. So what are the angles of reflection and refraction? Well, because it's more than the critical angle, that means that total internal reflection occurs and there's no refraction at all. So if you try to do Snell's law for this problem, if you try to plug in the 42.6, which is 1.5 degrees more than the critical angle that we found up here, and try to find the second angle, you're going to get a calculator error again. And that's because there is no refraction, only reflection. The law of reflection says that the angle of reflection has to be the same as the angle of incidence. So it's also 42.6 degrees. All right, red light has a vacuum wavelength of 660 nanometers. What is its speed, frequency, and wavelength of light in diamond, which has an index of refraction of 2.42? Well, the speed of light in some substance is the speed of light in a vacuum divided by the index of refraction. So in our case, that's 3 times 10 to the 8 meters per second divided by 2.42. So that gives us a speed of 1.24 times 10 to the 8 meters per second. And to find the wavelength in some substance is the vacuum wavelength divided by the index of refraction. So here that's 660 nanometers divided by 2.42, which gives us 273 nanometers. Now the frequency of light is the same in all substances. Doesn't matter if it's in the vacuum or air or water or diamond. So we can find the frequency using the vacuum wavelength and the vacuum speed, or we could have used the speed in this substance and the wavelength in this substance. We'll get the same frequency here. And that turns out to be 4.55 times 10 to the 14 hertz. All right, so long answer. So the only long answer question from this section would be a refraction / reflection question where we have a whole bunch of different layers. So if we just have one layer, there's just not enough content there for a long question. But if we have a whole bunch of different layers, then we could. So in this problem, we actually have 4 different layers. There's air, and then below the air are 3 different liquids. So there's oil, water, and below that there's syrup. Syrup. And so I've listed their indices of refraction there. And we know the light is incident on the oil with an angle of 22 degrees. So we want to find all of the angles of reflection and refraction. So there's more than you might think. So I've drawn this diagram here. There's a whole bunch of different ones. So up here, our θ1 is that 22 degrees. That's the incident angle when the light is traveling from the air into the oil. Now, part of that is reflected and part of that is refracted. So when the refracted ray comes down here and hits the boundary between the oil and the water, part of it is refracted and part of it is reflected. Now, this reflected ray also strikes a boundary, which means that part of it is reflected and part of it is refracted. Now, we could play this game a whole bunch of times, and this ray will ultimately hit here, and then part will be refracted and part will be reflected. But every single time light hits a boundary and it's reflected and refracted, then the light gets dimmer and dimmer and dimmer. So usually we'll stop at the second reflection. Okay, so we won't worry about what this ray does. We'll just find these angles. And similarly, this ray gets reflected and refracted. And then up here, it gets reflected and refracted again. So these are all of the angles that we want. And in each case, for reflection, we use the fact that the angles have to be the same. And for refraction, we'll use Snell's law. So between the air and the oil, we said that our angle of incidence was 22 degrees, which means that our reflected angle is also 22 degrees. And to find this θ2 that we have here, we'll use Snell's law. And so θ2 is the arc sine of the index of refraction of air divided by the index of refraction of oil times the sine of the incidence angle. And so that gives us 14.9 degrees. We can play the same game between the oil and the water. So this refracted angle that we just calculated was θ2. But if we drew this normal down straight, this triangle would be similar to this triangle. So our angle as measured from the normal here is also θ2. So it's also this 14.9 degree angle that we calculated. So the reflected angle has to be the same. So the reflected angle is also 14.9 degrees. And we can calculate our θ3 here with Snell's law. So I've done this here. It's the exact same as we did before. And so we find an angle of 16.4 degrees. Okay. Well, going on, once again, this triangle is similar to this triangle. So this angle has to be θ3, the same as this angle up here. So our angle of incidence is still this 16.4 degree angle. It gets reflected here. So this angle of reflection is also 16.4 degrees. Now to calculate θ4, the refracted angle, once again, we'll use Snell's law, and we'll find that it's 14 degrees. Okay, so this is sort of like the initial path of the light here that we've traced out. It gets refracted here, it gets refracted here, and it gets refracted here. Now, what about the reflected rays? They also meet at boundaries here, so we have to find these angles too. So let's see, which one did I do first? The water and the oil. So that would be this one that we're looking at. And so this triangle here, if we continue the normal, would also be similar to both of these triangles. So our angle of incidence here is theta 3, the same theta 3 that we calculated earlier to be 16.4 degrees. Okay. So this reflected ray is going to have the same angle because the law of reflection says they have to be the same. And we can calculate this theta 6 once again with Snell's law. So do that here. So it's the arc sine of the index of refraction of the water divided by the index of refraction of the oil times sine of theta 3. And that's because it's traveling from the water into the oil. Okay. And so that turns out to be what? 14.9 degrees. So we'll look at the symmetry of that in a minute. But now we can look at the oil and the air. So that's this ray here. So it's traveling from the oil into the air. So once again, similar triangles. This is also theta 2, the same theta 2 that we calculated here to be 14.9 degrees. So that means it also gets reflected at 14.9 degrees. And we can calculate this theta 5 with Snell's law. Oops. And so I've done that here, and we get 22 degrees. All right, now the symmetry here is important. So because all of these layers are flat, and it just keeps getting reflected and refracted, this theta 1 is going to be the same as our theta 5 here. It came in at an angle of 22 degrees, which means it's going to leave at an angle of 22 degrees. So similarly, our theta 2 here is going to be the same as our theta 6 here. So it came in at whatever theta 2 was, 14.9 degrees. So when it bounces back, it's also going to leave at an angle of 14.9 degrees. All right, so it's a long problem, but it's not a very difficult problem. All right, so next chapter, geometric optics and image formation. All right, so if an image is behind a mirror, it's a virtual image. And if an image is behind a lens, it's a real image. So I drew a little chart here. So here we have a mirror, and here's the front of the mirror. That's the side where the light is actually coming from, and then the back of the mirror. So this is the part that's actually mirrored, and this is just whatever's behind the mirror. So if an object is in front of the mirror, that means it's a real object, and so it has a real object distance. If an image is in front of a mirror, that means it's a real image and has a real image distance. Okay. Contrast that with the back of the mirror. This is the side where there's no light, the opposite of the mirrored side. And so if our object is back here, it's a virtual object. And so it has a negative object distance. And if our image is back here, then it's also a virtual image and has a negative image distance. All right, so we can contrast that with what happens with lenses. So it's the same for objects. Here's the front of the lens. This is the side where the light is actually coming from. If an object is over here, it's a real object, and so has a positive object distance. But if an image is here, that means it's a virtual image and has a negative image distance. So the back of the lens, this is not where the light is actually coming from. If the object is back here, then it acts as a virtual object and has a negative object distance. And if the image is back here, then it's a real image and thus has a positive image distance. So if we contrast mirrors and lenses, it's the same for objects. The objects have the same thing. If it's in front, then it's real and positive. If it's behind, it's negative and virtual. But the images are different. So if the image is in front of a mirror, that means it's real and positive. If the image is in front of a lens, that means it's negative and virtual, and vice versa for behind. Okay, so a negative magnification implies that the image is inverted. If the magnification has an absolute value that's less than 1, that means the image is smaller than the object. And if it has an absolute value greater than 1, that means it's larger than the object. Okay, so concave mirrors have positive focal lengths. That's true. And convex mirrors have negative focal lengths. Similarly, diverging lenses have negative focal lengths, and converging lenses have positive focal lengths. Okay. Now, of the mirrors that we discussed, only concave mirrors can produce real images. So remember what that means for a mirror. That means the image is in front of the mirror. Okay. Now, when someone looks at an object in a different medium than what they're in, so they could be in air looking at the water, or they could be in water looking up at something in the air, then that person doesn't see the object, they see the virtual image of the object, okay? So this statement was completely true. It just said real instead of virtual. It should be virtual. Remember, a real image is projectable and a virtual image is not. A virtual image is just what you get from tracing the light rays back to where they appear to come from. All right. So I have a whole bunch of these where we can draw some diagrams. Instead of actually drawing them, I just took some pictures from the internet so you can see what they actually should look like instead of my crude drawings. So we'll skip these. So we'll look at these in a second. So let's look at parallel light rays. What do parallel light rays mean? So parallel light rays are the rays that come from an object that's infinitely far away. If you have an object that's at a finite distance, then the light diverges from that. But the farther away it is, the less that light diverges. And so if it's actually at infinity, then it looks like the light rays are coming in parallel. Okay, so what does it mean if the image distance for a lens or mirror is negative? What about the object distance? Well, like we just talked about, if the distances are negative, that means you have a virtual image or object, whatever you're talking about. All right, so let's look at these ray diagrams. So I wanted you to draw several of them. So here's one for a converging lens where the object is beyond the focal point, okay? So here's the focal point. We can see that the object is beyond it. So we need to draw 3 different rays. One of them is parallel to our optical axis. That's this line that goes through the middle of the lens that the object sits on. So that one comes in parallel, and then it gets bent through the back focal point, okay? So that's what this first ray is doing. Our second ray needs to go through the focal point, and then it gets bent to be parallel to the optical axis, okay? So that's what this ray is doing. It goes through the front focal point, gets bent to be parallel. Our third ray goes straight through the lens and is unbent because it hits at a 0-degree angle relative to the normal. And so where all of these different rays converge, that's where our image is. So if we have an object that's beyond the focal point, then we end up with a real image. We can tell it's real because it's behind the lens. And we can also tell it's real because these light rays actually converge at this point. So if there was a screen here on this side of the lens, we could actually project an image of this object on the screen. So it's a real image and it's inverted. You can see it's upside down relative to the object. Now, where this one was drawn, this image is also bigger, but it doesn't have to be. It just depends on where the object is relative to the focal length. Okay, we can also have the object be in front of the focal point for a converging lens, which is exactly what we have here. So here's the focal point. Our object is in front of it. So we'll draw all the same rays that we did before. One is parallel to the optical axis. It's this line that goes through the focal points through the middle of our lens. and then it gets bent to go through the back focal point. Our second ray goes through the focal point. So that's what happened here. It went through our focal point and becomes parallel. Well, here our object is in front of the focal point, so it can't go through the focal point, also hit the lens. So we draw an imaginary line that connects the focal point to the top of our object, and then we keep going, and it gets bent to be parallel, okay? Then our final ray goes through the center of the lens and is uncurved, right? It just goes straight through. All right, now these rays clearly never converge. They keep getting farther and farther away from each other. But if we trace them back, then they all appear to originate from this single point here, okay? So we trace this one back, we trace this one back, and we trace this one back. They all start here. So because the light rays don't actually converge, and because the image is on the front side of the lens, that means we have a virtual image. It's upright because it's facing the same way as our object here, and it's enlarged, okay? All right, now what about a diverging lens? Well, for a diverging lens, it does not matter where the object is. It can be in front of the focal point or behind. We always get the same thing. So we'll draw our three same rays. One of them is parallel to our optical axis, this line that goes to the center of our lens here, and then gets bent to go through the focal point. That's what happened in both of these cases. Bent goes through the back focal point. Bent goes through the back focal point. Well, this is a diverging lens, so it doesn't get bent in, it gets bent out. So instead it gets bent out and looks like it came from the front focal point, okay? We draw this dotted line here. If we trace this back, then it goes through our focal point. All right, now our next ray is supposed to go through the focal point and then be bent to be parallel. Well, we already used up our front focal point, so we'll draw a ray that would go through the back focal point if it were to keep going, but instead it gets bent parallel to our optical axis, okay? So if we had just kept going, it would go through our back focal point, but instead it gets bent to be parallel. And then our third ray is exactly the same. It goes straight through the center of the lens and is unbent. Now, if we look here at A, B, and C, they clearly are never going to meet. So instead, we trace them back. So we trace B back like this, we trace C back like this, and we trace A back like this. And they all meet at this point. Now, the light rays themselves didn't meet. You had to trace them back, and it's on the front of the lens, which means we have a virtual image here. So we have a virtual image, and it's smaller than our object, and it's upright. All right, now what about mirrors? Well, we have two different types of mirrors. We have concave mirrors like this one. You know, it's concave because it caves toward our object. And then we have convex mirrors. Now, similar to what happened with our converging and diverging lenses, there's two cases for the concave mirror and only one case for the convex mirror. So here we have a case where our object is beyond the focal point. So here's our focal point right here. Our image is past it, okay? And now we're gonna draw the same rays that we did before. So one comes in parallel to our optical axis here. So this is the same axis that goes to the center of the mirror. So this first ray here is parallel, and then it gets reflected. Light obviously doesn't pass through the mirror, it gets reflected back. It gets reflected and goes through our focal point, okay? So that's what this first ray is doing. Now our second ray goes through the focal point and gets reflected to be parallel. That's exactly what this second ray is doing. And then our third ray hits the mirror straight on and bounces straight back. Now for this to happen, it has to go through the center of curvature. So the center of curvature is what the center of the sphere would be. This mirror is some piece of a sphere. So if we drew the whole sphere, the center of curvature would be the center of that sphere. That's right here. Okay. It's also at twice the focal distance. So here's our focal distance. Twice of that away is our center of curvature. And so our third light ray passes through the center of curvature and then bounces straight back. Now, all of these light rays actually converge at a point here, which means that this is our image. So it's a real image. We know that for two reasons. One, because the light rays actually converge here, and two, because it's on the front of the mirror. Remember, if you're on the front of the mirror, then you have a real image. So our image is smaller and it's inverted and it's real. All right, now what if we are in front of the focal point? So here's our object, it's moved up in front. We draw all the same rays that we did before. One comes in parallel, that's this blue one here. So it comes in parallel to our optical axis and it gets reflected to go through the focal point, okay? Now our second ray was supposed to go through the focal point and get bent to be parallel, get reflected back to be parallel. Well, we're in front of our focal point. So just like we did with our lens, we draw this imaginary line that goes through the focal point. So this ray looks like it went through our focal point, and then it gets reflected back to be parallel to our optical axis. Our third ray has to hit straight on and then get reflected and go through the center of curvature, okay? This is exactly what happened here, except for we had to go through the center of curvature before we reflected back, whereas here we're in front of it. But we still hit straight on, get reflected back, go through the center of curvature. Now, these rays are never going to converge. They get farther and farther away from each other as they move beyond the mirror. So we have to trace them all back. And if we trace all these light rays back, then they meet at this point. So this is our image. Now, this is a virtual image that's upright and enlarged, okay? You can tell it's enlarged, it's bigger than our object. We know it's virtual because it's behind the mirror and because we had to trace these light rays back to find where it was. Okay, so one more case, concave mirror. So convex mirror rather. A convex mirror bends the other way. So this is the front, this is the back, here's our optical axis. So we draw all the same rays that we did before. One of them is parallel to our optical axis here and gets reflected to go through the focal point. Now, for a convex mirror like this one, the focal point is behind the mirror. The focal point is always at half the radius, but since our mirror curves this way, our radius goes out here. So here's our center of curvature, and our focal point is at half that distance. So when this ray comes in, it gets reflected, and that ray looks like it came from the focal point. So if we trace it back, the dotted line goes through the focal point. Okay, now this is kind of a busy diagram, but our second one is supposed to go through the focal point and get bent back parallel. Well, once again, the focal point is behind the mirror, so we have to draw a dotted line that connects us to the focal point. So that's exactly what the second ray does here. If it had continued and there had been no mirror there, then it would go through this focal point. So it gets bent back parallel to our optical axis. And finally, our third ray hits the mirror straight on and then gets reflected straight back. So once again, if we draw a dotted line here, it would go through the center of curvature, just like our other ones that got reflected straight back in our other diagrams. Okay, now these rays are never going to converge, which means that we have to trace them back. And if we trace them back, then they converge at this one point here. So here's our image. It's upright and smaller, and it's virtual. We know it's virtual because it's behind the mirror, because we had to trace our light rays back to get to it. All right, so our next problem said, what happens if we have parallel light rays that strike our different objects? So for a converging lens, if parallel light rays come in, and they're also parallel to the optical axis, then they all converge on the focal point. Now remember, these parallel light rays means that they come from an object that's an infinite distance away. So if we had an object an infinite distance away from a converging lens, then the image would be infinitely small and be at the focal point. All right, what about a diverging lens? Well, these parallel light rays come in and they diverge away, of course. And if you trace them back, they look like they're coming from the focal point. Okay. So here, if you had an object that was an infinite distance away, you would have a virtual image. It's virtual because it's in the front, because we had to trace these light rays back at the focal point. All right, now what about our mirrors? Well, if we have a convex mirror, these parallel light rays come in and they all get reflected. And if we trace those reflections back, they once again come from the focal point. Okay, this looks like the source of this light that's coming out. All right. In a converging mirror, the light rays will come in, or rather a concave mirror. It is sometimes called a converging mirror, but whatever. These parallel light rays come in and they all get reflected to the focal point. Okay. So an object an infinite distance away produces a real image at the focal point. All right, so number 3, let's go back up and read the problem. A diverging lens is flat on one side and the other has a radius of curvature of 10 centimeters. If a 2.5 centimeter object is 22 centimeters away from the lens, and find the location and the size of the image. Is it virtual or real? And I left this part out. I supplemented it now, so your copy has this in there. But the index of refraction of the lens is 1.52. All right, so we have a diverging lens, which means that one of our sides here is concave, and we said the other one was flat, okay? Now, it doesn't matter which way you orient the lens. You could orient it this way or vice versa, where the flat side was toward the object. It doesn't matter. But okay, we said that this side had a radius of 10 centimeters. So if we had drawn this whole sphere here, it would have a radius of 10 centimeters. But remember, if we have a concave lens that's toward our object, it's concave toward our object, then the radius is negative. So R1 is negative 10 centimeters. And our backside is flat, which means that our R2 is infinite. Now, we can find 1 over the focal length of a lens with this equation. This is called the lens maker's equation. And remember, it only works in air. So the actual equation that's on your equation sheet is N2 over N1 minus 1. But if N1, whatever is outside of this lens, is air, then N1 is 1. And so we can just call N2 N, and we can use this equation. Okay. Now we said our lens has a radius of, or an index of refraction of 1.52. So we have 1.52 minus 1 times 1 over our first radius, which we said was negative 10 centimeters, minus 1 over our second radius, which was infinite. So since it's infinite, we have 1 over infinity. That's just 0, so that doesn't matter at all. So our focal length is all this stuff raised to the minus 1. Okay, so if we do that calculation, then we get negative 19 centimeters. Now, it's a good thing that we got a negative number because this is a diverging lens, and diverging lenses always have negative focal lengths. All right, so 1 over the focal length is 1 over the image distance plus 1 over the object distance. The object distance was given to us in the problem. So our image distance can be calculated as 1 over the focal length minus 1 over the object distance raised to the negative 1. So this is our 1 over our negative 19 centimeters minus 1 over our 22 centimeters. That was our object distance raised to the negative 1. So that gives us negative 10.2 centimeters. Okay, now we can find the magnification by doing minus the image distance over the object distance. And so that gives us positive 0.46. So we have a virtual image. We know it's virtual because we got a negative image distance. And since it's negative, that means it's in front of the lens. Remember, virtual images are in front of the lens. And then we can find the height of the image by multiplying our magnification by our object height. We said our object height was 2.5 centimeters. So it's 0.46 times 2.5, which gives us 1.2 centimeters. Now this is positive, which means that our image is upright. So we have an upright virtual image that's 10.2 centimeters in front of the lens. Okay, so let's go back up and read what number 4 said. So number 4 says we have a convex mirror that has a radius of curvature of 35 centimeters, and the same 2.5 centimeter object is 22 centimeters in front. Sorry, my dog was sitting on my TV remote. Okay, so we're doing number 4. We have a convex mirror that has a radius of curvature of 35 centimeters, and our 2.5 centimeter object is 22 centimeters in front. And we want to know the location and size of the image. Okay, so here's our mirror. It's convex, which means it's curved like this. So this is the mirrored side that had a radius of curvature of 35 centimeters. Now, because it's convex, that means our radius is negative, and our focal length is always half the radius. So our focal length is negative 17.5 centimeters. So now we know everything. We know the focal length and we know the object distance, so we can find the image distance. And so if we calculate that, we'll get negative 9.75 centimeters. Once again, we can calculate the magnification by doing minus the image distance over the object distance. So that gives us a magnification of 0.44. We can find the height of our image by multiplying that magnification by the height of our object. So that gives us 1 centimeter. So we have a virtual image. We know it's virtual because we got a negative number for our image distance. It's behind the mirror because virtual images for a mirror are behind the mirror. And it's 1 centimeters tall and it's upright. We know that it's upright because we got a positive number for the magnification and a positive number for the image height. All right, so time for the long answer problem. Here's the hard one. So we have a converging lens with a focal length of 5 centimeters, and it's 10 centimeters to the left of a convex mirror with a radius of curvature of 12.5 centimeters. A 0.5 centimeter object is 7.4 centimeters to the left of our lens. So where is the image formed by the mirror? What sort of image is it, and what is its height? Okay, so this is the situation we have. We have our object, which is 7.4 centimeters from a converging lens. And then 10 centimeters from that, we have our convex mirror. Okay. So what we do is we work this as 2 separate problems. We have an object and image distance for the lens, and we also have one for the mirror. So let's do the lens first. We were given the object distance and the focal length, so we can find the image distance the same way that we've done before. And we find that it's negative 28.5 centimeters. So this is a virtual image, which means that it's in front of the lens. So if we draw that again, it looks something like this. So here's our object. Here's the image formed by our lens. So this is our object distance for our lens. It's the L here. And this is our image distance from our lens. Now, the image acts as the object for the mirror. So this distance between the image from our lens and our mirror is our object distance for the mirror. Okay. Now, we don't know that distance, but we know the distance from the image to the lens and the distance from the lens to the mirror. So we can just add those together to find our object distance. And it should be positive. It should be positive because it's in front of the mirror. If instead we had an image behind the mirror, then we would have a negative object distance for the mirror. Okay. So the same equation works for our mirror here, but we need to find the focal length. We were told the radius of curvature, but not the focal length. But remember, those are related by a factor of 2. The focal length is half the radius of curvature. And since we have a convex mirror, it's negative. So our focal length is negative 6.25 centimeters. So we can find our image distance the same way we did before. we'll find that it's negative 5.38 centimeters. So since it's negative, that means it's behind the mirror. Okay. So here's our entire setup here. We have our object that's in front of our lens that creates an image that's back behind the lens. This image acts as the object for our mirror, and then another image is produced back here behind the mirror. All right, so we have two different magnifications occurring here. We have the magnification from the lens and the magnification from the mirror. Both of them are found the same way. It's the image distance divided by the object distance. Just make sure that you use the right ones. So for the lens, it's our image distance for our lens divided by the object distance for our lens with the negative sign. So that gives us a magnification of 3.85. And when we do the same thing for the mirror, we have a magnification of 0.14. Now the total magnification is the product of these. So we multiply our 0.14 times our 3.85, and that gives us a magnification of 0.539, okay? So the height of our object then is our 0.539 times the height of our object, which the problem said was 0.5 centimeter. So our image is 0.27 centimeters, and it's positive, which means that it's upright, okay? So we have a virtual image. How do we know it's virtual? Well, we know it's virtual because it's behind the mirror, or because our image distance was negative. Both of those things tell us it's a virtual image. Okay, so we have a virtual image. We found that it's 0.27 centimeters tall. Once again, that's positive, so that means it's upright, and it's 5.38 centimeters behind the mirror. Okay, last chapter, interference. So when waves encounter a small gap, they diffract because of Huygens principle. Remember, Huygens principle says that every point on a wavefront acts as a source for new waves. Now, normally they just go away and become the next wavefront. But if they hit a small gap, then that doesn't happen. They can't recombine like that. So you still have the spherical wave packet that's emanating out. And so it can bend around corners, or it can like go around sharp points or whatever. That's what diffraction is. All right, only coherent waves with the same wavelength can interfere. That is false. All waves interfere if they occupy the same space. But we only get pure constructive or pure destructive interference if we have coherent waves with the same wavelength. All right, if two sources of waves are independent from one another, they will be incoherent. That's true. So in other words, they won't be exactly aligned or exactly counter-aligned or have some permanent phase difference between them if they're emitted independently. All right, if light experiences constructive interference at some location, that location will appear to be brighter. That's right. The two waves sort of work together to make a bright spot. Their amplitudes add together, so they look brighter. On the other hand, if it experiences destructive interference, that location will be darker. So if they have the same amplitude, there actually will be no light from that spot at all. But in general, it'll be darker than the other places. All right, so when light reflects off of a surface with a larger index of refraction than the substance the light is in, it will undergo a phase change of pi. So remember, a phase change of pi means that all of the troughs become crests, all of the crests become troughs. So that's pi, not pi over 2. All right, when two beams of light are initially in phase, the quantity that determines whether the beams interfere constructively or destructively at some distant point where they meet is the path length difference, okay? So because they're initially in phase, when they meet again, if they're in phase or exactly out of phase or something in between, just depends on how much farther one beam went than the other beam. So if they went exactly the same distance, then they're still going to be in phase and they get constructive interference. If they go some integer number of wavelengths away, then they're still going to be in phase and they get constructive interference again. And if they go some number of wavelengths plus half a wavelength, that's the path difference, then they will destructively interfere and we won't see any light at all. Okay, the small angle approximation says that sine of theta is approximately tangent of theta, and that's approximately theta, not cosine. So cosine of a small angle is approximately 1, or 1 minus theta squared over 2, depending on if you want to keep quadratic terms or not. All right, short answer. So the short answer from this chapter are very straightforward. There's not really any curveballs that I could throw. It's just a straightforward application of the equations. So the only thing you have to ask yourself is it destructive interference or constructive? So our problem here says that blue light is incident on a pair of slits, which are 0.25 millimeters apart. And we have a screen that's 1.75 meters away. And we want to know at what angle is the third order minimum. So a minimum would mean a dark spot, which means destructive interference. So that's this equation here. For destructive interference, we have the extra half. For constructive interference, we don't have that extra half. Okay, so this is our equation then that can tell us this angle. And we want the third order one. So that means that m is equal to 3. So we just solve this for theta. It's the arc sine of all of this stuff. And we just plug in all the answers, all the quantities that were given to us in the problem. And we'll find that that angle is at 0.36 degrees. Okay, this is a small angle, but that's good because we want to use the small angle approximation. And we didn't use it here, but we'll use it in the next problem. All right, so we have the same experiment that was described up here. So the slits are still 2.25 millimeters apart. The screen is still 1.75 meters away. But this time we have a different wavelength of light. Okay, and so what we know is that the second order bright fringe is measured to be 0.98 centimeters away from the central bright fringe. So the central bright fringe is the bright spot that's right in the middle, right in between the two slits on the screen. And we want the second order one. So it's not the next bright spot, but the one after that, okay? Now, since we're talking about distances on the screen, we'll use this equation. And since it's constructive interference, we know it's constructive because this is a bright spot, we use just m. If it had been talking about dark spots, then we would have used m plus a half, okay? So we know all of these quantities here except for the wavelength, and that's what the question is asking for. So we just solve for our wavelength, which gives us this expression, and then we can plug in everything that we know. Okay, so we want the second order, so m is equal to 2, and ym was told to us in the problem, so 0.98 centimeters, and then everything else we know from the previous problem. Okay, so that gives us a wavelength of 7 times 10 to the minus 7 meters, or equivalently 700 nanometers. This is like a really red light. Okay, now something I didn't do, but I probably should have, is that this experiment is the one that showed to everybody that light really was a wave. So before Young did this experiment, everyone thought that light was made of particles because that's what Newton had said 150 years earlier. But this showed that it was wrong and that light is in fact a wave. This is also exactly how people measure the wavelength in real life. I mean, there's more sophisticated experiments now, but this was the first way that we were able to do it. And even now it's based on this basically. All right, so that's it.